Vibrations of Euler-Bernoulli beams. These are rod-like structures like this. The boundary conditions may be fixed in various ways. Properties are uniform along the rod. This boundary condition clamped on the left, free on the right is usually called cantilever. This is simply supported, pinned here and pinned here, pinned, pinned, pinned free. So that has a rigid body mode, this rotation, but other than that it has vibration modes. There is free, which has one rigid body mode like this and one rigid body mode like this and other vibration modes, clamped, and so on. There can be many boundary conditions. The mechanical, physical parameters are the mass and the length, which we also write m bar as the mass per unit length, and there is EI, which is the modulus of bending rigidity. The assumptions are plane sections remain plane and perpendicular to the neutral axis, familiar from strength of materials, and the bending moment at any section m divided by EI is equal to the curvature of the beam, which is approximately y double prime, and we write it here using partial derivatives because we are going to do dynamics and vibrations. This curvature is taken at any instant of time, t held fixed, and the moment at that instant. This relation m over EI equals y double prime or yxx is independent of acceleration. It applies even for a vibrating beam. The other assumption we make is that the translation or displacement of any part due to vibration has a more important role in inertia than the rotation of individual parts. This is consistent with what is sometimes called a long wavelength approximation, which indicates that the length scale over which the displacement varies is long compared to the thickness of the beam. So, for example, it would not apply to a vibration that looked like this. The equation of motion is the motion governing y seen as a function, equation governing y seen as a function of x and t. Here is a free body diagram of a small element of the beam. There is a downward shear force V over here, therefore it would be upward. It would change due to location, so it is V plus del V del x times delta x. Once again, this is a partial derivative with respect to x because we are doing dynamics. There is a clockwise moment here m, a counterclockwise moment here almost m, but with a small change del m del x times delta x. This point here is called A. Notice that the tilt of the beam is small. If you think of this angle as theta, then this angle of the V from vertical would be theta. Sin theta is approximately theta, cos theta is 1 minus theta squared by 2. What this means is whether you take V as slightly tilted or perfectly vertical, the vertical component of V does not change to first order. Also notice that there are no axial forces. So, in our linear momentum balance, we will look at vertical motions. We will take these forces to be perfectly vertical. Angular momentum balance about A, as we have said here, rotary inertia is to be neglected, and so the sum of moments about A should be 0. This V passes through A, it has no moment. This V is a distance delta x away, so it has a moment V delta x counterclockwise. This part del V del x times delta x contributes a quadratic term, so it is thrown away. This m is counteracted by this m and it leaves del m del x times delta x, that is retained. And so this is the net counterclockwise moment, that 0, which tells us del m del x is equal to minus V. Once again, this partial derivative with respect to x is taken because this is true at all instants of time. At each time when we hold time fixed, this is what is true. This is under dynamic conditions. Linear momentum balance in the vertical direction. The net force in the vertical direction is del V del x times delta x. That's here. This is equal to the mass, which is m bar times delta x, times the acceleration of that point, x held fixed, therefore del squared y del t squared. Once we cancel the delta x, we write del V del x is equal to m bar from here times this y double dot is the same as del squared y by del t squared. Now, this V is known in terms of m. This m is known in terms of del squared y del x squared. There is a minus sign here and these two are on opposite sides. So we take them on the same side, the minus sign disappears, and we have EI, then del 4th y by del x to the 4th plus m bar del squared y by del t squared is equal to 0, which we sometimes write as EI, then y with 4 primes to indicate the spatial derivative, plus m bar times y with 2 dots to indicate the time derivative is equal to 0. This is the equation of motion for the beam. Now let's look at free vibrations, which means we'll look for natural frequencies and mode shapes. This is a simple problem. There's just one beam, known length, no inhomogeneities, no point mass, no concentrated spring, nothing like that. So it is easier for us, you will see, to write x is equal to xi times L, such that xi, the non-dimensional variable, goes from 0 to 1. Del x of anything now becomes 1 by L times del xi of that thing. So over here the del to the 4th y by del x to the 4th becomes del xi to the 4th, and this 4 L's come out. Now we seek solutions of the form y is phi of xi times sine omega t. We substitute this into this equation here. Over here we get a minus omega squared. When we move it to the right hand side, that's what we get here. So this equation becomes this equation. These 4 derivatives are here. The sine omega t has been cancelled. This m bar L to the 4th by EI times omega squared. These are physical parameters. This is an unknown that we are trying to find. This whole thing together is called beta to the power 4th. Beta is just this new parameter or variable, this new quantity we have to find. It includes the unknown omega as well as physical parameters. This here now is an ordinary differential equation. So we write its characteristic equation. It's r to the 4th is beta to the 4th. That means r squared is plus minus beta squared. That means r is plus minus beta as well as plus minus I beta. This means again that the solution for phi is some constant times a times sine beta xi plus b times cos beta xi plus c times sinh beta xi or hyperbolic sine beta xi plus d times cos beta xi or hyperbolic cosine beta xi. A, B, C and D are as yet undetermined constants. This much is true independent of boundary conditions. This much is true whether it's a cantilever beam or a simply supported beam or anything like that. Now to find A, B, C and D, we have to look at the boundary conditions. The simplest case is the simply supported case. Let me remind you, that means it's pinned here and here. These points can't move. In between it can take arbitrary shapes. For this reason we know that there is no rigid body mode. It's fixed here and fixed here. That means we know that beta is not equal to 0 because omega cannot be 0. The 0 displacement here and here are written as phi of 0 is equal to phi of 1 is equal to 0. And the 0 moment here and here is written as 0 curvature. So phi double prime of 0 is equal to phi double prime of 1 is equal to 0. When we take this boundary condition phi of 0 is equal to 0, that means we come here and we put in xi equals 0. This sine becomes 0 anyway and the sinh becomes 0 anyway. The cos becomes 1 and the cosh becomes 1, and we are left with b plus d is equal to 0, which is what I have written here with this one corresponding to this one. This 2 corresponding to this 2 involves second derivatives. We come here and take second derivatives. The second derivative of sine is minus sine with a multiplier beta squared minus cosine, sinh and cosh. Once again we put xi is equal to 0, the sinh and the sine become 0. These remain, but this one gets a minus sign and this one doesn't, and there is a beta square multiplier. Beta square multiplier. And so I have beta squared minus b plus d is equal to 0. Since beta is not 0, I have minus b plus d is 0 and b plus d is 0. I can add these two equations, find 2d is equal to 0. There is just nothing we can do. D has to be 0, therefore b has to be 0. This much is now determined. Now we look at this condition, which is phi of 1 is equal to 0. When we do that, what we find, b and d being 0, we have established that, so we drop them. We have a sine beta plus c sinh beta has to be 0. That is what I have written here. Now we look at this derivative, second derivative condition phi double prime. When we take the phi double prime, what we have is a beta squared and a negative from the minus sign, so a minus a sine beta plus c sinh beta. So this is 0, and we know that the beta is not 0. So taking this equation here and this equation here, assembling them in matrix form, we get sine beta sinh beta here and here times a and c here and here is equal to 0, and similarly minus sine beta and sinh beta here and here times a and c here and here is equal to 0. I am denoting this coefficient matrix with this hash or pound sign. A and C both 0 are not interesting because B and D are also 0. We need non-trivial solutions. To have non-trivial solutions, the determinant of this coefficient matrix must be set equal to 0. The determinant happens to be 2 times sine beta sinh beta. Since beta is not 0, therefore sinh beta is not 0. Therefore sine beta has to be 0, which means beta is n pi. If we take beta is n pi or sine beta is equal to 0 and come back to this equation, for example, or this equation, when we come back here, we find that sine beta is 0, so A remains indeterminate. C sinh beta is 0, but sinh beta is not 0, that means C is 0. So we have established that B is 0, C is 0, D is 0, A is indeterminate. It will remain indeterminate because the mode shape is an eigenvector of the system. It is indeterminate up to a scalar multiple. A is that scalar multiple. So we come back here again. Remember, beta is n pi, and the mode shape, which is sine beta xi, beta is n pi and xi is x by L. And so the mode shape is sine n pi x by L. Let's look at other boundary conditions. First, the cantilever or the clamped free case. Phi is 0 at 0, that means the displacement is 0. Phi prime is 0 at 0, that means the slope is 0, it's clamped. Phi double prime at 1 is 0, that is because the bending moment at this end is 0. Phi triple prime at 1 is equal to 0, that means the shear force at this end is 0. These 4 again into the A sine beta x plus B cos beta x plus C sinh beta x, not even x, xi, plus D cos beta xi. When we put this one in there, we get one equation, another, and another 4 equations. These 4 are written like this. Just as we did for the simply supported case, we can work it out by hand, but I find it simpler to do it systematically in this way. So this coefficient matrix is some function of beta. The unknown coefficients are A, B, C, and D. It's a homogeneous system of equations. This determinant must be set equal to 0. When we set it equal to 0, we get some equation in terms of beta. It has infinitely many roots. We find those one by one, as many as we need. For each such beta, when we substitute it in, what happens is this coefficient matrix is singular. So therefore, 0 is an eigenvalue. Corresponding to that eigenvalue of 0, there is an eigenvector. When we find that eigenvector, it gives the proportions of A, B, C, and D. This is an approach that works in all these cases. So that's what I am doing. I have done these calculations separately. You can work them out as an assignment. And so the cantilever or clamped free case leads to this characteristic equation: 1 plus cos beta is equal to 0. The clamped pinned case, so clamped means phi of 0 is equal to 0, phi prime of 0 is equal to 0. The pinned case means the displacement is 0, so phi of 1 is 0 and the moment is 0 at the pinned end. So phi double prime is 0. You put it in, calculate this determinant, simplify it, and this is what you get. Sine beta cos beta minus cos beta sinh beta is equal to 0. Here's another one, clamped. So clamped means 0 displacement, 0 slope. Clamped at the other end, 0 displacement, 0 slope. We get cos beta minus 1 is equal to 0. That's what we get when we work it out. Here is free. 0 moment, 0 shear at the left end, 0 moment, 0 shear at the right end, and we get 1 minus cos beta is equal to 0. You will notice that these two are the same. This is very interesting. The free case has two rigid body modes, one like this and one like this, but then the first frequency you find subsequently, the first non-zero frequency is the first frequency of the clamped beam. I will comment on this a bit later. Here is a pinned free. Pinned free, pinned means displacement is 0 and moment is 0 at the free end, and moment and shear force are 0. I am sorry, displacement and moment are 0 at the pinned end, moment and shear are 0 at the free end. This leads to sine beta cos beta minus cos beta sinh beta is equal to 0, which is the same as this one, the clamped pinned case. But let us look at this one is easy. We have this equation, we have phi with 4 primes is beta to the 4th times phi. We can differentiate this equation twice and then we will have 6 primes here and 2 primes here. Then we can define a new variable psi, which is phi with 2 primes, and what happens is this second equation is simply the old equation for phi. This seems like a trivial game, but then what happens, you see, is that where phi double prime is 0, now we expect psi to be 0, which is here. And where phi triple prime is 0, we now expect psi prime to be 0, which is this boundary condition. And the same for these two. And so the way it works out is that the betas are the same because the governing equation is the same and the boundary conditions are the same. So there is this intuitive way to see why the clamped and the free have the same natural frequencies. Why the clamped pinned and the pinned free have the same natural frequency seems more subtle. I don't have a simple intuition for it. There is something else that I would like you to see, the complementary relation between rotation and moment and displacement and shear. So you see over here, the displacement is 0, therefore the shear, we are not saying that it is 0, the shear can be anything. Over here the rotation is 0, so the moment can be anything. Over here the displacement is 0, so the shear can be anything. The rotation can be anything, therefore the moment is 0. In this way, wherever we constrain the displacement, there we don't constrain the shear to be 0. Where we don't constrain the displacement, there the shear is 0. So either the displacement is 0 or the shear is 0, and either the rotation is 0 or the moment is 0. These are the simple cases that we have studied. Now we will look at orthogonality of mode shapes. So let us borrow an intuition from the multi-degree of freedom case that we have studied, where for some finite dimensional situation the kinetic energy is half x dot transpose mx dot and potential energy is half x transpose kx. We get some eigenvectors, and those eigenvectors satisfy this orthogonality when weighted with the mass and stiffness matrices. If m and n are not the same, these inner products are 0. We have seen this. Here the kinetic energy is half times the integral from 0 to L in terms of the x variable, x the spatial variable is m bar y dot squared, and the potential energy is half EI times y double prime squared. And so we may expect from the kinetic energy, just like this orthogonality, we may expect that phi m phi n integrated is 0, and by analogy with this stiffness matrix, we may expect that phi m double prime phi n double prime integrated is equal to 0 when m is not equal to n. Let us work it out and see if it is actually true. So here is the first one. Imagine that beta m, now again I am working in the xi coordinate. X and xi are just different by a factor of L. It really makes no difference. Since we have worked this out, so we will work here. Here is the one eigenvector phi m corresponding to some beta m, another eigenvector phi n corresponding to some beta n. This one is 0, this one is 0, m is not equal to n. Let us take this left hand side, which is 0, multiply by phi n and integrate from 0 to 1. Since this quantity is 0, the integrand is 0, so the integral is 0, but we write it as two parts. So this one here times this remains on the left side, this one here times this goes over to the right side. Now let us simplify this one by integration by parts. When we do that, we take this as the first function, or whichever we take, I guess we take this as the first function. So this one comes out, this one gets integrated. So I have phi m triple prime phi n and then a minus, and then this triple prime here and this one differentiated here is to be integrated. Now you see here, this is a condition on the shear force and this is a condition on the displacement. Due to the complementarity that we have just noted, what happens is every eigenvector either is itself 0 or has its third derivative 0 at both 0 as well as 1. This is the complementarity we were considering. Therefore, this is 0 here, and this term is nothing, 0. So now we have this integral, we come here, integration by parts again, and what happens is this negative, then this one integrated phi double prime and phi prime, and then with the plus phi m double prime, phi n double prime. Now we look here, this is a moment and this is a rotation. So at both ends, either the rotation is 0 or the moment is 0, this term is 0, and therefore this quantity here works out to be this integral, the product of the double primes. Therefore, this integral product of the double primes phi m double prime phi n double prime is equal to beta m to the fourth phi m phi n, beta m to the fourth phi m phi n integrated from 0 to 1. But I could have done exactly the same thing with the second equation, and then I would have got beta n to the power 4 prime phi m phi n. The fact that these two are equal, if beta m is not equal to beta n, it means the integral of phi m phi n is 0. If the integral of phi m phi n is 0, then since this is equal to this one here, this integral is also 0. This is what tells us that these two orthogonality conditions that we anticipated are in fact true. In the finite dimensional multi-degree of freedom case, we had this mass weighted or normalization. So for the same eigenvector, we can scale them so that this integral is 1. Usually when we are dealing with some problem with the physical length, it may be convenient for us to scale it so that phi m squared taken as a function of x integrated from 0 to L is 1. We can always normalize them like this. Now let's consider dynamics with external loading. So here is a portion of the beam. On it there is a distributed upward load W of x and t, varies with space and time. There are some boundary conditions of the sort that we have discussed so far. To get the equations of motion, you can think about it two different ways. One is, if you think of beam statics, then from strength of materials, you know EI times Y with 4 derivatives is W times W of x. If you want to use statics and do dynamics, you can use D'Alembert's principle or use inertia forces, in which case this you replace with the inertia force, which is minus MA, only over here on a per unit length basis. Alternately, you can draw a free body diagram, do linear momentum balance again, the same that we have already done, except you include this W of x and t over here. However you do it, you end up with this equation of motion, the same as we had before for the unforced thing and some forcing on the right hand side. So here is our governing equation. Some initial conditions for the beam have to be given. So the beam at time t is equal to 0 was in a certain shape, and its velocities must also be given. So y0 of x is the shape, and v0 of x is the function representing the velocities at the instant t is equal to 0. These are the initial values. There are of course boundary values, and now we are interested in solving this problem forward in time. We will assume that y of x and t, the solution, can be represented as a linear combination of the mode shapes. This is what we have done in the multi-degree of freedom case, where we had n independent eigenvectors. Over here we are basically not proving but assuming that these eigenvectors make a complete basis. Over here I have written the eigenvectors as functions of x, not xi, but x and xi vary just by a factor of L, so that should not be confusing. This is an infinite sum. At any instant, the shape of the beam is known. It can be represented as a linear combination of the mode shapes. As the shape of the beam changes with time, the coefficients in the linear combination must be treated as functions of time. So that is the basis or reason or justification for our representation of the solution in terms of these modal coordinates. Once we do that, we have to find the initial conditions for the A's, and that is easy enough because y at x and 0 is ak at 0 times phi k of x summed over k. So here is that sum and here is y. This thing, both sides, I take it in the square bracket. What I do is multiply by phi n of x and integrate from 0 to L. And because of my orthogonality, what happens is phi k times phi n, the integral is 0 unless k is equal to n, and when k is equal to n, the integral is 1, so it gives me just a n of 0, that's here. And the left hand side, y0 of x comes out over here, integral from 0 to L, y0 of x times phi n of x. I have to find this integral, there is no escape. Once you find it, that's the initial condition. Similarly, v0 of x or v0 of x, this is y dot. Y dot means over here you see is just ak dot and then time t equal to 0. So whatever ak dot is at time t is equal to 0 is to be found. That appears in this sum over here, ak dot at 0 times phi k of x summed over k. This sum is equal to v0. I put it inside curly brackets. What I do similarly is I take the curly bracket, multiply by phi n of x, integrate from 0 to L, and I get a n dot of 0 is equal to the integral of v0 of x from 0 to L, v0 of x times phi n of x. In this way, the initial conditions are known for all the ak's. Ak as well as ak dot are known at time t equals 0. So now the governing equation, we substitute the series solution. So ei, and here is y with 4 primes, note the x. Here is m bar and here is y double dot. This is equal to w of x and t. Now these phi, they are the solutions to our eigenvalue problem. So ei times phi k with 4 primes is actually omega k square times m bar times phi k. So when we take this into the sum and put it here with the phi k, what happens is it becomes omega k square phi k. So here is the ak and omega k square phi k, I'm sorry, I forgot the m bar. So omega k square m bar and the phi k is here. And this term here is m bar ak double dot, the whole thing multiplying phi k summed over k. This is equal to w of x and t. What do I do now? I multiply the left and right with phi n of x, integrate from 0 to L, thereby eliminating x. This side I get omega n squared m bar a n of t plus m bar a n double dot of t. On this side I get the integral of w of x and t from 0 to L multiplied by phi n of x dx. Remember, there is a free parameter here n, it's integer parameter depending on the mode shape that I've used. X is now a dummy variable of integration. It is eliminated. And so what I get is some function of t with an index n. I'll call it fn bar of t. The bar is simply because there is still an m bar here. When I divide by the m bar, then I'll call it fn of t. And that is just omega n squared times a n here and a n double dot here. I've changed the location because this is how we normally write our harmonic oscillator. And you can see that this a n is now just a harmonic oscillator. It is a n double dot plus whatever is the omega n squared times a n is fn of t. They are all decoupled. In this decoupling, there are some things to watch for. So here is an example with the simply supported case where we can draw the eigenvectors. So here is the first eigenvector, sine pi x over L. Here is the second one, sine 2 pi x over L, the third one and the fourth one. For all the even order ones, you see that the mode shape is 0, the eigenvector is 0 at the midpoint. So now if W is a concentrated force at the midpoint of the beam, what will happen is that the integral of that concentrated force times whatever time variation, that concentrated force times phi n is going to be 0 for all the even modes. And this means that in these equations there will be 0 on the right hand side. The even modes will not be excited. And so they will not be excited as per linear theory, but even in practice they may be excited very weakly. Okay. Now let's come back here. If the rapidity in time with which w of x and t varies is bounded, that means w of x and t, it does not have hammer strikes, but it's sort of slowly varying. Finite variation. It can be 2 hertz or 200 hertz or 2000 hertz, it doesn't matter. But some finite bounded rate that you know in advance and you fix. Okay? So if that happens, then Fn of t also has only a bounded rate at which it varies in time. And then what happens is this varies with some bounded rate, but this omega n square gets larger and larger and larger. Remember, for example, for the simply supported case, beta was n pi, right? So if beta was n pi, then beta to the power 4 is omega square, beta square is n square. So the nth natural frequency is proportional to n square. In this way, omega n square is pretty large. It gets very large very fast. And therefore, what happens, remember the single degree of freedom system, what happens is this Fn does not change very fast while this omega n square gets larger and larger and larger. It's like a harmonic oscillator with the stiffer and stiffer and stiffer spring. And what this means is for the higher modes, the response is pseudostatic. It is almost like the single degree of freedom system excited at a near zero frequency. And then what happens is this part becomes irrelevant, this part dominates, and so An is essentially Fn by omega n squared. And because omega n squared itself is small, see, for the simply supported beam, omega n squared is like beta to the power 4, beta is n pi, so this is n to the power 4, it's very fast. And so what happens is the contributions from the higher modes go down very rapidly, and therefore the higher modes can often be neglected. So if you have some structure on which there is some excitation about which you know in advance that the frequency content is limited, for example, wind excitation on a bridge, cars passing over a bridge, water forces on a rod, things like this. If you know in advance that the frequency content at higher frequencies, the energy is low, then what happens is you can neglect higher modes and keep a finite number of modes. And that is a motivation for the multi-degree of freedom theory that we have done. So in fact, almost all practical problems will be solved using some multi-degree of freedom approximation. If you are designing the structure, trying to find the maximum amplitude, trying to develop a controller, trying to damp the vibrations, in all such things, you will usually use a finite number. You could use a small number of modes and stop it there, or make other approximations as we have discussed in class.